Hi everyone. Had a request for a video from Dave Mountain. Hopefully I've got your question correct, so I thought why not cover everything to do with it. I believe it's been experimented with several years ago. I'm pretty sure I remember some videos about it when I first started with FE. Let's explain it in a bit more detail. So the question was, again, assuming I'm understanding your question correctly, Dave, to explain what happens to the magnetic field if a electromagnetic coil, like this one, had a steel outer jacket on it as well as a core. I believe that's where you were going. Now this one is the very first coil I ever wound. It's had a partial refit for the core, for want of it better. As you can tell by the side walls, not brilliantly wound, but pretty darn close. But anyway, what happens when you stick a magnetically conductive jacket around it? Well, this is where we go to paper. And we'll try not to kill the camera. Right. Okay. Might just look a little bit weird. Again, don't forget, the proportions are not exactly accurate. So we have the standard iron core, and we have the wires. Again, this is a two-dimensional cross-sectional area, and not what happens in a full three-dimensional coil, basically. Now, around this, we have these two, which indicate this is just this cross-sectional area indicating the outer jacket. Right. Basically, as I've already explained, a magnetic field likes to travel through magnetically conductive material, ferrous material. Right. It's easier, it's more dense, etc., etc. So, what basically happens is you get a small field that comes out there, then this bit expands. Oh, Jesus. Oh, there's a lump there in my desk. And this side goes over to here. Basically looks like that. So what happens is, at these points here, the magnetic field, instead of expanding that way, they actually condense at that point, travel along the outer jacket, and then do the same thing towards the back. Like that. Now, there may be some field that is, well, I wouldn't say escaping, but I would say running along the surface of the outer jacket. Same as the inner one. Well, I say outer jacket, it is a jacket, it's also a core as well. Now, here comes the fun bit. You're gonna love this. Right. Let's assume this end is, because of the way that it's all wound, is producing a north field. Yeah? Yeah, I've done it nice and bold so you can actually see it over the where I've drawn the flux line. We therefore then take the other side as south. Okay, relatively speaking. Well, what happens to the jacket? Well, those people that have followed my videos will have looked up the left and right hand rules, and basically what happens is at this point here becomes south. It is the opposite because it's on the opposite side of the turns. It becomes opposite. So it goes here, and then here is north, and north on there as well. So you get a nice nice packed, dense magnetic field between these two, but the problem is you get an opposite field here. Now the other part of Dave's question, if I am reading his questions correctly, is I think he's experimented with it and found that it killed the rotor speed and didn't really work very well. Right, that question has two parts to it. So first of all, the first answer is because you've got opposite fields adjacent to your drive field, which if we take a standard Bedini monopole, right, your drive field is the north, you've got the south fields right next to it. If these fields are too close to the magnet when it pulses, it just negates everything. The fields just get screwed up and you don't get any push from it. In fact, the other side of the first answer is that because you have a magnetic jacket over this, the magnet, as it's moving away, gets attracted to the outer, and then it wants to stay near the outer. So you've got a huge magnetic mass dragging your magnet to one point. So it can be inefficient. The second part of the answer to his question, which is the question as to why it doesn't work very well, also has to do with density, and that is of the core. Right, now the shall we go the Holy Bible way of winding a electric coil is to use rods that go from one side to the other. Smaller the better. Right? This is because it straightens out the field lines and it stops the coil alternating and doing some funky stuff. Now the other thing is, anyone that's experimented with coil sizes knows that if your core is too thin, right, or it is too haphazard and doesn't straighten out the field lines properly and yada yada yada, they know it causes huge problems when trying to pulse it with, say, something like a standard Bedini SSG, that is. So if you don't have enough in the centre, then basically it starts self-oscillating, doesn't start, field lines go all over the place, doesn't work, and is, well, if it does work, it's extremely inefficient. However, if you get too much in the centre, it has another effect. Now I'm going to go into this in this video, because it's kind of all into one. Was originally planning to do this in a completely different video, but hey, oh well, let's chuck it in on one and see how many people are still landing afterwards. Okay, if you have the right amount, then you get a wonderfully efficient electromagnet. Great, lovely. If you have too little, field lines don't get straightened and nothing works right. If you have too much, you get a different effect. There are two things that happens when you have too much. Number one, it takes longer to energize the core, basically to establish all the field lines, make everything flow from north to south, south to north, etc., etc. But not only that, if you have too much, it's too dense, you actually reduce the total strength, if I can put it that way, of the field. You still get the same quantity, but you reduce the strength. Kind of difficult to explain that one. It's all to do with the size of your core. If you use the same material between a core that's a normal size and a core that's twice the diameter, if you use the same type of material, you'll find the one that's twice the diameter will be weaker than the smaller one, than the normal sized one. It's all to do with field size, etc., etc. Same total volume that's coming out, but it's just coming out of a bigger hole, like a pipe. You take a hose pipe, nothing on the end of it, turn the tap on, you get water coming out an even flow. Stick your thumb over the end and reduce it by half, you get a nice long spurt with an arc on it, but it's pretty much the same physical volume, it just comes out faster. Same thing for the core. Right? So if you have an excessively thick core, right, you get a thick centre field here. Right? Same quantity, it just comes out slower, for want of a better way of putting it, speaking magnetically. Now, when you're dealing with basically a double core, an inner core and like an outer jacket core, which is what Dave's now asking, you're increasing the total, this part has two explanations as well, thinking about it. You're not only increasing the total amount of magnetic material near the core, right, which again you have to take into account. If you've got too much of it, then too much is absorbed. But you also have to make sure that this outer jacket that you have on there is comprised of rods that go from front to back and back to front, exactly the same as the core. Basically, so that the flux lines that come back here, that come from there, get conducted along rather than spat out at weird angles. So you have to make sure that it's properly conducting down its length. Now the other thing is, you are going to lose a little bit of efficiency, as you always do with cores. Rough guess, I believe you can hit about 98% efficiency with a core. Now, it may be possible to get higher, but I mean, most people that build these things, you're probably looking at 85% typically. If you take your time and you do everything nice and neat, etc, etc. But please, higher efficiency is much better for the core. So, just to recap, the outer jacket is an inverse of the core in the terms of fields, but it has to have the same properties. So if you were making an outer jacket for your core, then my initial recommendation would be to use the small iron rods. And again, I say iron rods, it all just depends on what material you're actually using. I have obtained a roll of the iron wire. As you can see on this one, it's not exactly, it's not been smoothed down and secured, but you can see the iron rods in there. They're very small, they're 1/2 mil. Right? Smaller iron rods, more density, but also they help to keep the flux line smoother. But you do need to chop that off straight down. Bit like that end. That's not too bad, just needs another doing. Okay, same goes for around the outside. Right. Remember, your rods go that way with my pencil. Turn it around so we can get some light on this. So you can see the cord there, and there's my pencil indicating the direction of the rods. If you wrap the rods in the same as if it was you're winding the steel wire, the copper wire rather, then that's not going to work. You're just going to scatter the magnetic field, and then it's all game over, basically. So, needs to go front to back. Right, a bit like the laminations on a old school transformer. I mean, if you look into transformers, basically they would have a figure of 8, for want of a better word, that goes around them, so there's a full conductive path, so the magnetic field doesn't come out into basically the air and the surroundings. It's all put in one go, which I may be able to show. There we are. Just so happen to have an isolation transformer on my desk. If you take a look, there's the, in this case it's an iron ferrite type thing, but that going round here, all the way around this yellow band as it is, which is insulated, right, is the outer, and then if you look here you can actually see the separation between the two cores. Now you can't see it directly, but there's another bar of ferrite going through, so it basically creates a conductive ring from north to south and south to north for it. So nothing is ejected, for want of a better word, into the surroundings, anything that's around the component as it's sat on the PCB.
In our case, we want a field to form at each end, or at one end at least anyway. But what most people have a trouble with is this gap here. It's too close for most setups. I mean, essentially, if you got this distance right, with the distance between your magnets, now depending on how you have your rotor, if you were using a standard monopole rotor, then you get a, for want of a better way of putting it, a virtual south field that's halfway between your magnets. If the distance between your magnets was to equal that distance, then the core, centre core, would sit in the virtual south pole. Hint, hint. So, using a small coil on a big rotor with lots of space between magnets, this type of setup isn't going to work. You have to match the distances, right? Which is why in these videos I do not give you figures, because number one, you don't learn anything. Number two, it's all the figures for everything you build, right, is for your setup. If you choose a 5mm rotor, 5mm shaft for your rotor, that dictates what types of rotors you can use, what types of bearings, etc, etc. So unless I gave you all the dimensions in one go, all the strengths, and I wound your coils for you, and I hand-picked your magnets and hand-picked your bearings and so on and so forth, then any figure that I give you here, actual figure, is just going to be pie in the sky. It's going to be for my setup only. You know, so unless I give you everything and build it for you, then the figures that I give you are irrelevant. However, I can give you relative sizes, roughly. Now, another thing that's by the book, or the Holy Bible, whichever you want to call it, is the core size. Some people say the core size should equal the size of your magnet. Some say it should be 25% bigger. Some say it should be 25% smaller. What is the truth? The truth is, it entirely depends on what you're doing. That's the whole point of the free end groups. Yeah, okay. I'm just going to blanket them all in one go. The whole point is experimentation to find out what works for you. What works for one person doesn't necessarily work for another one. What I've almost always told people to do is to make your core size equal your magnet size. Is that the right way of doing it? It's a good starting place. I've always told people to experiment on sizes. I mean, as you can see, going back to this one here, you can see the core size. This is just a bog standard plastic spool that you get enamelled copper wire on. Strangely enough, I don't know how the hell this coincidence has actually happened, but these dimensions are pretty good starting place.
at least for beginners. So that's what you start off with. The problem is, if you then go to this and you add these on the outside, you've just increased the amount of magnetically conductive material, right, without reducing your core. You have to design your coils based on what it is you're doing. Total masses, number of turns, dimensions, magnetic material, quantity of magnetic material, and even down to its shape. Almost everyone does cylindrical coils. Now, there are people playing with starship coils and Rodin coils and whatnot. What can I say? Mapping those things is just nigh on impossible. It needs to be done with a computer. Certainly cannot be drawn on a piece of paper, so don't ask. Although, having said that, I am tempted to have a go. Just to be the first. Anyway, so going back to this, you can't just take a core that works well and then add to it and expect it to work just as well again. So anyone that wanted to have a play with this, what I would recommend doing is shortening the length being the distance from North and South Pole, but making it wider. So it looks a bit more like a Tesla pancake coil. Thinner in terms of north to south and wider. That way you can also easily control the amount of magnetic materials at various points. Now, a slight extension to Dave's question. I don't think it's been done recently, but I'm going to talk about it anyway. What about putting steel between each layer of turns? So like an iron sort of foil, something like that. Yes, you can, but you're going to significantly increase the amount of magnetic material, and unless you get that foil perfect, you're going to completely screw up the fields. Okay, so you need to have it in straight lines, perfectly straight lines, no crinkles, no contamination, and so on and so forth. The closer you put magnetic material to your windings, the more critical it is that it's perfect magnetically. So bear that in mind. That's why on a standard reel coil, the one that I've been showing all the way through this video, actually has about 1 to 1.5 mil gap between the copper windings and the core. Is that gap important? The distance is as important as all the other dimensions on the coil. That's what I'll say. Right. Is the gap itself important? Yes, it is, because it can help. Same goes for on the outer. You need that gap there. So hopefully, touch wood, this has turned into a half-hour video of me rambling on. Hopefully that answers Dave's questions, and touch wood, be useful to everyone else as well. Another one of Dave's questions was actually extremely complicated, so keep your ears perked for my next video. I don't know if I'll be able to do it today. Might be first thing tomorrow morning. Touch wood. Hopefully within a couple of days, because it is a darn good question, and it'll make soup out of people's brains, which I love doing. So keep your ears perked, plenty of experimenting, and have fun. Bye for now.